Let's look at one of the applications of AC circuits. Let's consider a special case that we've looked at already before, where we have a voltage source and we have a resistor. And now let's consider here a circuit element. And what we want to look at is what is the output voltage across this element compared to the input voltage of our voltage source. And in particular, we would like to study the relationship of the amplitudes of the output voltage versus the input voltage. Now, when we made a DC circuit and we put a resistor here, so we had two different resistors, this is what we call the voltage divider. So we're generalizing the concept of a voltage divider to an AC circuit. And in particular, what we want to consider is the following idea, that suppose we have an incoming voltage, an amplitude, and it's driven sinusoidally with angular frequency omega, that in fact we may have, for some reason, many input voltages coming into our circuit network, and they all have different angular frequencies. And what we would like is that our output voltage can filter out, say, certain of those frequencies, filter out the high frequencies that are input, maybe filters out the low frequencies, or only lets a band of frequencies pass through. How can we analyze that and design a circuit that will do that? Well, our first case that we're going to look at is where our circuit element in here is just a capacitor C. And let's analyze the output voltage compared to the input voltage for this case. Well, we know that all we have to do is get the equivalent impedance of this circuit, which is the resistance minus I over omega C. And our current that comes in has an amplitude I naught equal to the incoming voltage divided by the magnitude of the equivalent impedance. And you can see that that's simply R squared plus 1 over omega C quantity squared to the 1/2. Now the phase, recall, is, if we wrote this as an amplitude and a phase, the phase is what we had before, inverse tangent of the imaginary part minus 1 over omega C divided by the real part, R. And that analyzes the current that comes into this. Now, what we'd like to look at, though, is what is the output voltage. So we write our output voltage in the following way. Let's write V out has amplitude. It still has a sinusoidal phase given by the driven frequency. And here we'll have a slightly different phase shift. Now, we know that because the current is running through this, that V out is equal to the impedance of this element, the capacitance times the current. And if we wrote all this out, we would get V out naught e to the I omega t e to the minus I beta is equal to minus I over omega c times e, the amplitude of the current, which will just keep things I naught e to the I omega t e to the minus I phi. Now, first off, we have the same cancellations as we had before. And recall that e to the minus I pi over 2 is equal to minus I. So what we have here is V out naught e to the minus I beta is equal to I naught over omega c. There's the real part. We have phases. We're canceling the e to the I omega t. So it's e to the minus I phi plus pi over 2. So there's how we've analyzed it. And so we see that V out in amplitude is I naught, which we've solved for as V in naught over the r squared plus 1 over omega c squared to the 1/2 times another factor of 1 over omega c. And notice that beta is equal to phi plus pi over 2. So there's a phase shift of 90 degrees across this capacitor. But we want to focus more on the ratio V out naught over V in naught, which is equal to, now here I can do a number of different things, but I'm going to bring the omega c quantity squared inside, and I get 1 over omega c r squared plus 1 to the factor 1/2. Now, if I were to plot that function, let's look at the value. So let's make a plot here where we're going to plot omega, and we have V out naught over V in naught. And let's look at the values where omega is very small. Well, then this term goes to 0, and we have just equal to 1. So then as omega gets larger, this plot falls off. And when omega becomes very large, then this term effectively becomes 0. And so what we have here is what we could refer to as a low-pass filter. For very large omegas, the ratio of the output voltage to the input voltage, and we're talking about magnitudes, goes to 0. For omega equals 0, it's just 1. And for small values of omega, most of this amplitude ratio is a large fraction, a 0.9, 0.8, 0.7. And so what we see is that these low frequencies pass through this filter. And if we had another circuit out here with some load, then the input to this rest of the circuit is been filtered, and only the low frequencies pass through. So that's an example of what we call a low-pass filter.